Hello everyone, welcome to today's webinar. We are the EECONE project and we are all about reducing electronic waste through innovation and collaboration. My name is Moritz Schlagmann and I'm very happy to be your host of today's webinar. And I want to welcome you all on behalf of the EECONE project and thank you for joining us today. So what is the main challenge we are addressing? The global and the European e-waste is growing and growing, and we have to keep up with it. The problem is that the e-waste growth by a factor outgrows the recycling and proper handling of the e-waste by a factor of 5. So we at EECONE have the vision of developing technology for a zero waste future of electronic components and systems. And our four key objectives are defining green ECS, making green ECS, and showcasing green solution. And last but not least, building consciousness. And this we are doing by applying the 6R principle to every use case we have. And we aim to close the resource loops, to reduce the waste, to create products that align with the principle of circular economy. So we're always looking into reduction, reliability, repair, reuse, refurbishment, and last but not least, recycling. And today we present you 3 use cases that in which we are doing it. So the first use case will be presented by Olivia. It's about repairability and recyclability of power electronics in the automotive industry. The second one is about healthcare, presented by Mani and Sabine. And the third one is about green IoT devices, where we look also into modular design and reducing of components. This is presented by Raúl. So please, if you have any questions, please feel free to put them in the chat. And after the 3 presentations, we will go over it and have a short discussion with you and hopefully answer all your questions. And with that, I'm handing over to Olivia.
Hello everyone, I'm Olivia Belorgeot. I'm working in the Schaeffler company as a lifecycle engineering specialist, and I'm also for the EECONE project manager in the company. So I'm working mainly on innovative solutions about eco-design, circularity, and lifecycle analysis. So today I will present you the use case 2 and the first results that we obtain in the first period and focusing on repairability and recyclability of power electronic products as part of the automotive sector. So first, some words about the company. So Schaeffler is a motion technology company. So with the motion at the connecting element. So we are 120,000 employees worldwide. So we have lots of different locations. So you have 250 locations with 55 different countries. And we are a really innovative company as we have 34 R&D center. And me particularly, I'm working in the R&D center of Toulouse in France. So in the company, we have 8 product families. We are going from the bearings to the repair and monitoring services. But today we will talk mainly about the power electronic units because it's the topic of our use case 2 in the EECONE project. So let's move on the topic of today. So the use case 2. So the use case 2 is focusing on power electronic products designed for reducing the amount of e-waste. And the motivation that we have in this use case are really to try to reduce the environmental footprint of our power electronic products and also to improve the repairability and reuse of this kind of product in order to decrease the amount of e-waste. We have so defined 2 different KPIs in this use case. The first one is to have a 25% reduction of e-waste compared to the current generation of power electronic products, so with the new generation. And we want also to allow the repair of individual PCBs by making them 100% removable, because today we have some problematics in the product to be able to remove the PCBs. So you can see here on the right the different partners that are working on the use case 2 with Schaeffler. We have some partners from industry, but also from research institutes and so on. And what I want to highlight also is that in this use case 2, we are working on 5 different R: the reduce, the reliability, the repair, the reuse, and the recycle. So only the refurbish is not in our focus. But today, we will not talk about the 5 R's. We will talk just about the repair and the recycle and the first result that we obtain. So mainly recyclability and disassembly constraint of an inverter first. And the second topic will be on repairability constraint of an onboard charger and DC-DC converter. So first topic on the recyclability. So here we had a collaboration between Schaeffler and Recycling, that is a partner of the EECONE project, and that is a PCB recycler, where we wanted to investigate how it's possible to improve the recyclability potential of a product that is already on the market, and so that has already a frozen design, and a design that was not with the objective to facilitate the recycle at the end of life. So we decided to study an inverter product on the market, and we sent 2 products to recycling to analyze how is it possible to dismantle the product and what are the constraints that we have today if we want to recycle it. So basically, here you can see on the pictures the different parts of the product that were dismantled. And we achieved to dismantle 3 parts of the product in 15 minutes. So 15 minutes is quite high if we want to apply this recycling process to a high level, a high volume of products. But at the end, we are able in 15 minutes to have on one part the DC-DC converter parts, so with transformers, ferrite, and 2 PCB that are glued at the bottom of the box. So basically here, if you want then, for example, to recuperate the transformers, you have to put more effort to remove it from the coating, for example, in the box. And on the other parts, so the second part that we are able to separate in 15 minutes is the power module here. So the power module here, it's an aggregate of the power module with the bare die chips, but also with the cooling plate below. And then you have a DC-link capacitor that is glued also to the cooling plate. So if you want to have just the power module, also you have to separate the cooling plate and the DC-link capacitor. But today, it's not as simple as it is because, for example, the power module is soldered to the cooling plate. So we have some constraint if we want to recycle the power module. Then the third part that we are able to dismantle in 15 minutes is the rest of the box. So with the cover, with all the individual PCBs, with all the screws, and yeah, you have everything then dismantled. Just to highlight the fact that we also try to identify the global recyclability rate of the product. So it was based on an estimation of recycling based on their experience. So what they did after the dismantling, they decided to sort the different parts and to identify some material category for each part. So for example, the housing, okay, it's aluminum alloy. For some other parts, it will be a mix of metals and plastics. For PCBs, is intermediate PCBs and so on. And so based on these categories, they estimate a global recyclability rate of 86%. I want to be careful with these figures because here the global recyclability rates was based on just the material composition. We didn't take into account here the complexity to dismantle the product, to separate some parts from others. So we should be at something a little bit lower. But yeah, it's quite encouraging that we have lots of metals in the product, and so we are able, if we want to put the effort, to recycle the different materials. So we identify the different constraints that we have in terms of recyclability, so in terms of material composition, but also in terms of disassembly of the product. And what I want to highlight today, because we don't have lots of time to discuss about that, but are the main eco-design recommendations that we define based on this analysis. The first one is to limit the alloys or the composites that are costly to separate. For example, nickel or steel alloys, that's some alloy that will contaminate the mixture. For example, if we are deciding to just shred the wall inverter, then it will be more complex to recuperate some rare metals. Also, for every mixture of metallic and plastic parts, for example, here it will also decrease the recyclability rate when you have mixture of plastic and metals. So it leads to the second eco-design recommendation, that is avoid as much as possible. So overmolding PCBs, for example, because you are adding more plastic in the product, but also glued or solder parts. Because today, as I said, if we have some plastic parts that are glued to metals, we go from, for example, 100% recyclability rate with aluminium to 80% of recyclability rate when we have plastic glued to this aluminium. And the third recommendation, is to make easily accessible parts with specific recycling processes, like batteries, but here, for example, like power module, because here in the power module, we have the most valuable metals with rare metals like copper, gold, palladium, and silver. And as it is today soldered to the cooling plate, it's complexify the recuperation of the rare metals. So if we want to recuperate this value, we have to think about all the way to assemble these two together. Let's move on the second topic, the repairability constraint of an HV box. So an HV box in our company is basically a combination of an onboard charger and a DC-DC converter. So we have two functions in the same box. And here, so we had a collaboration with Ampere from the Renault Group, where we did an analysis on the HV box about the potential of disassembly with the objective to repair. So we did first a benchmark between the Schaeffler HV box, the VMAX, so a Chinese manufacturer, and the Tesla HV box. And we analyzed the product architecture complexity of the product, and also how it's possible to dismantle the product without damaging the different parts. So based on this analysis, we identified some repairability challenges in power electronic products, and we present this in a congress, the EECONE Congress, EECONE Powertrain Congress, where we wrote a paper also. So if you want to have more information, maybe I can share this paper with you later. And so the main result that we obtain in terms of repairability challenge is that we identify that for the first repairability challenge is the mechanical structure. So how the box is closed and how the box is sealed. Today, for example, in our HV box here, the mechanical structure is considered not repairable because we have a liquid sealant, and when we want to open the box, we need to put lots of effort, and when we are achieving to open the box, it will damage the cover, the housing, the external connectors, and also some parts inside the box. So basically, if you want to repair, it's not the right solutions. Second is the connections for the external connector fixation. Also, are they sealed to the housing? How they are connected to the PCB inside? And you have also the internal connections that are mainly how the PCBs inside the box are connected together. Is it with soldering or is it with male-female connectors, for example? And the third repairability challenge is the thermal management in the box. So how the components are cooled. So is it with thermal paste or podding? Both of the solutions are not really compatible with repair because you have to put lots of effort to remove the components. And then you have also to put lots of effort to clean everything if you want to have a clean repair. But then, based on this repairability challenge, so as I said, we did the benchmark with different products from some competitors. And we did the spider charts where we compare the repairability, the lean architecture, and the power density of each product. And we saw some, contrary way to do things. So, for example, when we have a product that has a high power density, it seems to go in the contrary of repairability. It will be very difficult to repair the product. And on the contrary, when we have a product that has a simple architecture, so something not really complex, then it will be easier to repair it. So it's some things we should think about when we want to do repairable design. And so I want to highlight that repairability will require also compromise. So with the architecture complexity, but with the power density, reliability, and also the cost, because sometimes repairable solutions are more expensive. So last slide, it's about the next step about our work. So as I show you today, we have some work done on recyclability of the inverter, and the next step are to investigate the environmental impact of PCB recycling process. And on the HV box, that is a product that is under development, based on the repairability challenge analysis, we want to investigate a modular design for the converter, so that will be that will facilitate the repair and the maintenance of the product. And we will also investigate, so with the NP Grenoble, some interconnection solution to go with this modularity. So with some soldering concept between to interconnect two PCBs together. And to overcome the challenge on mechanical structure, we will lead some work on debonding solution for liquid sealant, so to find some alternative to the sealing of the box. So thank you for listening, and if you have any questions, don't hesitate to ask now or to contact me at my email address. Thank you.
Thank you very much for the nice overview in the field of automotive and what we can do. And I can see that's really a challenge in terms of repairability, but complexity and handling everything together. It's not easy, but thank you very much for taking this step and looking into it. And I think this is the most important part, that we progress and learn new things. Thank you very much. So if you have further questions, please put it in the chat. We will go over it after the next two presentations. And with that, I would hand over the stage to Mani and Sabine.
Hello, everyone. I'm going to start the presentation on eco-conscious diabetes monitoring, or the use case 6 within the EECONE project. Mani and I will be presenting together. Today I had a maternity last year, so we split up the project management. So I started it, then Mani took over, and now I'm back at it. basically the goal of this project is to work towards sustainable point-of-care health monitoring devices. We picked diabetes monitoring because it's a really high-profile, high-volume product that was really important. And we both are giving the presentation today, but there is a large team behind it, and we'll show you the institutions as well. And particularly, we need to mention Emily Becerra as well, who is doing a lot of work on the project as well. Okay, thank you. So just to introduce us a little bit, we call Silicon Austria Labs. We are an R&D center with a focus on the development of electronic systems. We're relatively new. We're located in Austria, as obvious from our name. We're not just working on silicon, even though we're called Silicon. We have industry-oriented research, R&D services, research infrastructure available, including very large research clean rooms. And we have, particularly in the group that we work in, we have competences in advanced sustainable and organic materials for electronics, printed electronics, and lifecycle analysis and eco-design of electronic systems. So we work on the sustainability sector quite a bit as well. Okay, so the motivation behind designing this use case, I just want to explain a little bit. Medicine is very strongly moving towards point-of-care sensors. So sensors where you can analyze things relatively quickly, and where you do not need to send things into labs. So basically hospitals can analyze them, even GPs or other doctors can analyze them in their offices, but also not even point of care. So there is also a move towards devices that can be used for medical purposes in their own homes, and even continuous monitoring can be applied. So these devices are great because they significantly advance health, they significantly advance the individual health, personal health, but also they really help the healthcare systems to basically save money as well, in a sense, because by early monitoring, you can prevent escalation, escalation later down the line. So this is great. What the problem is here is that these devices create an enormous amount of e-waste. So if you take a look and you look at the iStat, for example, which is from Abbott, I picked two devices from Abbott because it's a huge medical device company. But if you take a look at this, then you've got a reader, yeah, but you've got also like a cartridge, and this cartridge is full of electronics. This can be only used once. It's used once and then it's thrown away. And this contributes to the pile of e-waste. There's another device that I'm showing here. This is a wearable device for diabetes monitoring from Abbott. So basically this is our competition, even though we are obviously not as far as Abbott is. But this device is also, it's a device that can be worn for a couple of weeks, but then it needs to be thrown away. It's a wearable sensor for glucose. So there's a huge issue, but also a huge market potential to make these throwaway bits more sustainable. They have, sorry, if you go back, sorry, the picture that I'm showing is a picture from Sierra Leone, and that's from a publication which investigated e-waste. And you think about, yes, okay, if they're in a hospital, why don't we just throw away this cartridge and we recycle the electronic components, which would be at a point of care even easier to do than at home. However, actually 1 in 3 healthcare facilities globally, and here we're looking at global perspectives as well, does not segregate their waste. So you cannot actually see, so here's a picture of Sierra Leone, and that's basically, that is a hospital waste, and that is being sifted through. So there's no waste segregation, and it's basically, yeah. So adding to the global pile of e-waste, even the healthcare industry is one of the, I think if it was a country, it would be the 5th largest emitter in carbon emissions. So it's a large polluter that is obviously important, but is also making a huge impact. Now, thank you. So perfect. So the objective of our use case, our device, which has reduced materials, modularity, so you have a reusable part and a recyclable part, and then a usable and recyclable part, but that is basically that's also biodegradable now.
Bine, we've lost you for a second.
Yes.
Maybe turn off the camera. Maybe then the connection is more stable.
Sure. So we have basically a sensor patch. That is a sensor patch that is biodegradable. It's made from a biodegradable substrate. It's made from carbon-based inks. It can sense glucose, pH, and potassium, which are important markers for diabetes. And it has a sensor designed to minimize dimension. So this is the sensor patch. And you can take out a fresh sensor patch from your package every time you need to monitor. And this sensor patch is biodegradable. And then we have a chip patch. So you stick the sensor patch onto the chip patch, and you can stick a new sensor patch on maybe 20 times or even more. And this chip patch has all the printed interconnects, antenna, and flexible integration. And most importantly, it also has nano or bio-based packaging. We're still working on this, and it has a single chip solution, which makes it also much more sustainable than having like a very large reading device. You can read it out with your cell phone, so there's no readout device really required. So it's based on a modular system with detachability, and reusing the chip patch at least 20 times. That was our KPI, and having a 90% e-waste reduction. Okay. So the question is here, we're asking, what if we could make this device so that it has biodegradable parts, etc.? Obviously, it's not at the market, it's not at market level yet, but we just want to ask the question and try to use as much as we can of sustainable materials. So the partners involved in use case 6 are Cynano, which is a company which works on bio-ink formulation. Then we have Saal and CSEM in Switzerland, who work together on the sensor patch development. Then we have Infineon, CSEM and Saal, who work together on developing this chip patch, so a battery-free wireless electronic system. The CSEM and Infineon, who work together on the energy management of the chip. And Fraunhofer ISC, who is developing material for encapsulation that is bio-based. And then Orbotech, which is a company in Israel, and they're working on defect repairs. So they're working on basically when we print on copper to make these prints better. Okay. I just want to show you as my last slide, and then Mani will take over, that we are working with eco-design. So we base our design on LCA results. We use the 3D experience environment, which is provided by a partner in the EECONE project as well. So that's Dassault System, the 3DS environment in which you can basically fully integrate an LCA and eco-design collaboration space. We're working with EcoInvent, and we're doing a cradle to grave assessment. So if you take a look at this, we have 3 cases that we compare. The conventional one, this is an image from a publication that we based our conventional case on. Then an improved one where we use a single chip solution, but the sensor is not made from biodegradable materials yet. And then we have the ideal case for us, which is a single chip solution on sustainable materials, where we really work with bio-based materials, which Mani will explain you in a bit. Okay. If you look here at the assessments, you can see there's life cycle assessments. I've only pulled out 3 indicators. This is kilogram CO2 produced, a disability adjusted life years, and basically the environmental footprint points. And you can see that even going to just a single chip solution, which takes away the whole added components, already improves the life cycle assessment results enormously, and it even gets better when you go to the sustainable materials. Okay. And this is also why I can show you, if you see how the impacts are split over the different materials, just in environmental footprint points, you can see that the very, very large impact is coming from the PCB here on this one. So basically starting to remove this is already making the whole thing more sustainable, but we can be even better. And the goal is to go carbon negative with algae-based substrates, for example, which will give a carbon negative footprint. Okay, so Manny will go an overview and tell you a bit more about technical details of the project now.
Hello everyone, I'm myself Teja Vijjapu. So far Sabine have introduced about the overall use case and the objective and the motivation. So I'll take over from here to discuss more about the technical aspects of the use case. So ultimately what we are aiming to develop is a modular hybrid and two component sensing system. So it comprises of biodegradable sensor patch, which is aimed to detect biomarkers in the interstitial fluids. So which is minimally invasive, and we are aiming to develop a sensor patch using biodegradable substrates, and these are like electrochemical sensors, and they are aimed to develop like multi-analytes within this interstitial body fluids. And the next component of the sensing system, and the essential one, is the reusable chip patch. So as Sabine mentioned here, we are aiming to use this chip patch for at least 20 times. So, and this consists of different modules that enables this sensing system works. So essentially it consists of a measurement and data acquisition module. So it is used to connect with the sensor patch and perform electrochemical measurements and does the data acquisition. And then it chip patch also has a management as well, energy management and data processing module. And so once the chip patch performs the measurement, process the data, and it communicates with the user through the smartphone. Here we are not using any additional electronic component, which is like conventionally all these point of care sensor uses. So we are using the smartphone as an ultimate device for the user to interface, and this smartphone will also be used to harvest energy. So we will have a supercap or battery, which is we are in the which is still under the progress of development. So we gonna harvest energy from the smartphone through NFC, and we also communicate with the chip on the perform the measurement and get the data analysis to the smartphone. So this chip, the essential component is the microchip. And coming to the sensor patch, so as we mentioned, we are aimed to use this sensor patch for single use. So we wanted to make it biodegradable because we're gonna use like more sensor patches than the chip patch. So we are aiming to develop these electrochemical sensors on cellular substrate as well as algae substrate. So primarily we are focusing on the cellular substrate. So these are the sensors that we have developed on the cellular substrate. You can see this. And the same thing we are aiming to develop like for multi-analyte detection. So we are going to have 3 working electrodes within the single sensor patch, and they are going to be biofunctionalized with the help of CSEM. And this sensor patch, we are also exploring to use algae as a substrate material because algae is abundant a lot in the sea, and this is highly sustainable. So we have also demonstrated this algae-based glucose sensors on, and it is also published, and you can see the results, and it is linear for until 15 millimolar region. So our solution is a single chip solution, having the application-specific integrated chip enables to develop a hybrid sensing system. So this microchip is developed by Infineon. It has all the essential modules to enable this electrochemical measurements and data processing and communication interface. So these are the various interfaces that chip has, and it also has an inbuilt microcontroller to perform everything. So this chip can do almost every process that is needed for this. So having this chip, we can able to develop a hybrid potentiostat. Here, hybrid means we are using a printed technologies as well as microfabrication technology. So that's why I was using this a term called hybrid. So microfabrication technologies means to develop this microchip. So as I just mentioned, so Infineon chip enables the development of the printed chip patch we chose this printed technology because inherently this printed technology is sustainable because it is an additive manufacturing technologies and uses less material when compared to the traditional PCB technologies, where it is more of substrate to manufacturing. And this chip patch will be interfaced with the sensor patch through a mechanical connection or a bioadhesive. So we are still exploring the best possible way, either through a mechanical connection or through a bioadhesive. And this chip patch will perform electrochemical measurements and other processes that I mentioned. So we ultimately need encapsulation because we are having this chip patch on a flexible substrate, and it needs to be protected from the environment and the humidity and multiple aspects. So for this, we need an encapsulation. Even we are exploring the use of biopassivation using like bio-based encapsulation coatings. So these bio-based encapsulation coatings are being developed by Fraunhofer, and this ink will be coated on the chip patch again through printed technologies as an encapsulation layer. So to conclude, so coming to we are aiming to develop the eco-conscious diabetes monitoring patch, and the innovation highlights are we are developing this ink, graphene inks with food grade binders for low and also for low temperature curing to develop a sensor patch, and they develop this carbon active substrates for printed electronics and eco design of modular and hybrid sensing system, and we are developing copper-based printed potentiostat in general and sustainable encapsulation methods, and we are developing sustainable interconnection methods for modular biomedical sensing system. And overall, we are improving the environmental footprint of the sensing system. So the main highlight is the excellent collaboration with multiple organizations within this use case. Thank you.
Cool. Thank you very much, Sabine and Mani. Great overview. And I think one of the fields where you can see there's a lot of necessary e-waste production, a lot of necessary waste production, and where we can try to make it better and step towards the goal of a zero waste future. So I'm also looking forward from any of the participants, please, if you have any messages, any questions, please put it in the chat, and we will answer them after our next presentation from Raúl. And I would hand over now to you. The stage is yours.
Okay, thank you, Moritz. My name is Raúl Arnau from TST. Well, I'm presenting very briefly, and I hope that not getting very much into the technical details of our EECONE use case 10, which is titled Green Soil Proof Technologies for Greener IoT Devices in Agriculture, which is a bit of a spoiler of the contents. And just to give a brief overview of our initial motivation to develop this use case, it's important to say that it addresses a topic of great concern to Europe and worldwide in general, which is the environmental protection of soils. And it's mentioned in most or many relevant strategies regarding environmental and climate crisis, including the European Green Deal, Farm to Fork strategy, and there's also one which specifically targets European soil sustainability. These strategies will set ambitious goals for the following years, including a 50% reduction of pesticides use and nutrient losses in soils by 2050, and also a 20% fertilizer use. On the other hand, besides strategies, new digital technologies considering the digital transition strategies too, are powerful tools for achieving the goals of the Green Deal in regard to soils, particularly by providing better environmental monitoring and also data for better informed decision making and policy implementation at policy level. And in particular, smart farming and the use of soil information systems are based on deploying connected devices in the field, many devices usually, to collect information. And this also implies a substantial increase in the number of electronic devices expected in the following years. And this could have a negative impact on the goals that are well defined in the sustainable and climate environmental challenge strategies. In particular, if this sustainability of electronics is not carefully considered. And from a more practical perspective, our use case revolves around a TST product, which is an IoT sensor, a part of Bayer's nematode system, which is devoted to nematode pest management, mostly in greenhouse crops. And this probe is a wireless temperature sensor that provides periodic readings of the temperature of the soil at 20 centimeters depth. And it's currently a product which is mature and well tested, and it counts on battery and has an expected operating life between 2 and 5 years. And also it's being deployed in around 50 countries with several thousand of units working now. And this IoT product is used in the use case as a baseline for the innovations which are being developed by the joint effort of several partners. The objective of the use case is to develop, investigate in the design and develop tools and methods for the design of more environmentally sustainable digitalization technologies and applied to agriculture. It involves reducing electronic waste generation and also minimizing its impact, both from a cost and an environmental perspectives. And regarding technical objectives, this use case involves the development of a couple of tools, one for the estimation of the remaining useful life of batteries, and another for the selection of batteries from an environmental perspective point of view, I mean. And this one includes also an option for no battery use at all. And also from the perspective of design of new elements, of new components of these IoT solutions, there are contributions for the design and development of less hazardous batteries. Also, this already mentioned battery-free alternative. Also, the modular design or redesign of the probe, the baseline probe, the use of more sustainable materials, optimized housing, and from the recycling perspective, the development of new, more sustainable recycling processes for lithium primary batteries. Our ambition in the use case is that all these innovations contribute to an overall e-waste reduction by 30%. Besides, we expect to improve the reuse of components by 5% and the improve of the recyclability of the whole device, but more in particular, its batteries and also reducing the battery waste. And in order to develop these innovative tools and methods, a group of research entities and enterprises, including both SMEs and large enterprises, we are working together in close collaboration. and each contributing from their particular fields of expertise and fields of work, well, including the selection and management of batteries, development of new batteries, recyclability aspects, both from the perspective of electronics and batteries, mechanical design, and more sustainable materials for both the housing and PCBs, and also the development of new tools. And well, in order to establish a baseline for the comparison, no, and to reference our new developments, the product, the baseline device, has been carefully characterized, considering functional, technical, and operational aspects. And this one includes also the architecture and identification of the main components of the probe, and also its materials and modes of operation, consumption per mode, and so on. And this overall characterization of the probe serves as a reference against which to compare the technical developments and innovation carried out in the project, and allowing also to estimate our progresses and to estimate or compute our indicators. And well, getting a bit more into the detail of the architecture of the probe, as you can see in the picture on the left, in this diagram, it's quite simple. The design includes only one PCB that it includes the main electronic modules, which are the microcontroller, communications, informative LEDs, and activation switch, which is magnetic, and the conversion from analog to digital, the information of the transducer, and a power supply. And all this together with the power source, which are primary batteries, and a supercapacitor, are enclosed in the housing of the probe. And outside you can see the temperature transducer that we are using, which is a PT100. And also, well, the operation of the probe has been carefully analyzed, in particular from a power consumption perspective. And well, once we set our objectives and analyze the baseline, we started working on the development of each of these proposed innovations. And in the slides hereafter, we'll see, well, very briefly, an overview of the different approaches and achievements obtained so far. And this one is an overview of the modular design approach. And for this one, we have, well, analyzed and identified the applicable or feasible standards in terms of interconnection, and in particular 3 that we consider most promising, which is the one used in Raspberry Pis, Arduino Nano boards, and ESP32 development kit. And well, we end up selecting this Raspberry Pi hat, which comes from hardware attached on top, as a standard for the modular design of the boards, which well, are electronic. All this one single PCB is being broken down into 4 smaller modules. And we selected this hat standard because, well, mostly because it's very popular, and also because there's a wide range of commercially available add-on boards that can be used to extend and the functionality of new designs. And the objective of this modularity, this breaking down a single electronic piece which works fine and is very well tested, is double. First, to facilitate repairs, and also for making recycling easier. The original architecture, as I said, it has been split into 4 modules. The figures on top, these 3 ones, are, well, the microcontroller communications and RTD converter at design stage, and the figures, the pictures on the bottom are those modules already implemented, and the one on the right is the power module during some tests. In terms of sustainable materials, we have carried out a comprehensive analysis of the state of the art of sustainable materials for electronics, and from this analysis, we established 4 categories, addressing each one different parts of the electronic boards, which are the substrate, interconnections, solderings between the interconnections and electronic devices, and the coating. Well, very briefly, from each of these categories, a series of requirements were distilled, well, taking into consideration as restrictions for the comparison the operating conditions, requirements of the baseline proof, no? I mean, to maintain the intended functionality of the device, and most promising materials were filtered and prioritized. And in this slide, you can see that we, for the case of the substrate of the PCBs, we have already selected a couple of these commercial materials, which are Arboform and Bioflex, both sustainable for and suitable for large scale production, and also compatible with injection molding. And in this slide is currently we are, well, after redesigning some of the already redesigned PCBs of the new modules, we are working on the implementation of these ones in sustainable materials. In particular, the RTD to digital converter module, and also the power module. And here, well, maybe it's worth highlighting that the PCB complexity and the manufacturing processes are playing a key role in achieving this. And in this slide, well, there's a very brief overview of one of the main tools of the use case, which is the battery selection tool. And well, we started analyzing the state of the art also of the different methodologies and metrics that are used in scientific literature to assess the life cycle of lithium-ion batteries. And now we are currently working on a methodology that takes advantage on the 3DS experience platform of Dassault to describe the components, materials, and also to help us estimate metrics for the comparison. Well, in EECONE, several batteries are being considered, including the baseline using the probe, and also new prototypes of greener batteries being also developed in this use case by CCM that uses less hazardous materials and processes, and also a battery-less option, which is also another tool developed in EECONE, the feasibility assessment of this battery-less solution. And it has, well, its own dedicated analysis, including datasets and procedures and metrics. As a result, so far, 2 metrics are being considered in the assessment, which are reliability and the repairability. And in this slide, very briefly, also another tool, the battery remaining useful life estimation, which objective is to estimate the charge or current charge of the small lithium batteries, and it focuses on the estimation methods, considering the limited computational power of an IoT device. And so far, well, the approach is double. One using data-driven approach, machine learning tools, which are LSTM together with a large language model to capture the spatiotemporal relation and predict in a. And the other one is an empirical model, which is based on this careful characterization of the effective capacity of the battery, taking into account the different operational modes of the probe. That's a duty cycle measurement. And both tools are almost finished. And
we're running out of time, unfortunately.
Yeah, I'll be very brief. I think I have only this one slide and another. And I think that these are, well, very interesting developments, which are the battery itself and the process for recyclability of the batteries. And well, I must say that in both cases, the battery has been already developed, a prototype, and it seems to show, well, an important reduction in both cost and environmental impact. And well, that besides the battery is easier to recycle. And in terms of the processes, well, one difficulty of running these recycling processes is to obtain enough black mass from batteries. And well, currently we are working on that and running a baseline recycling process to establish the reference for comparison. And I'm done. Thank you, Moritz, and everyone.
Thank you very much for the nice overview. Yeah, it's a completely different field. Also coming from this point of care sensors and healthcare to healthcare for plants, a big step, but nevertheless, very, very interesting. So thank you very much for the overview. I guess we are already over our time, but we have two questions in our chat. So to the presenter, Olivia, maybe you can briefly address the first question from Thomas, which is about would it be necessary to exclude certain materials to get better recyclability? But then he addresses, he fears that the lifetime may be reduced significantly. So this is kind of a trade-off. Therefore, I think the reduction of specific materials have to be balanced with the lifetime. Any comment on that? How to implement this in the development process?
Thank you, Thomas, for your good question. I totally agree with you that, yeah, we have to do the balance between the reducing of lifetime of some products when we find some other alternative of materials. For me, when we are searching the alternatives, really the objective is to still answer to the specification of the product. So we are trying also to investigate not even just the environmental impact, but also the reliability and the quality of the product at the end. And I think for me, when you want to integrate some eco-design solution in a product, really the important thing is to check this with a life cycle analysis. And when you are doing a life cycle analysis, you are doing it on all the cradle to grave, so on all the phase of the life cycle, so with the production, but also the use phase and the end of life, to be sure that if your materials, for example, don't have the same lifetime as the current one, then you can compare it. And then when you have the same functional units of the same lifetime of your product, you can see that you have to, for example, produce 2 parts with these new materials if you want to reach the 15 years of lifetime, for example. So for me, it's really important when you are doing eco-design solutions to check it with life cycle analysis during the development process and to compare between the new design and the actual design. So yeah,
so really take into account the lifetime, even the new materials. Yeah.
Yes, but if it's not answering all your questions, you can reach me by email and we can continue to discuss about it.
Perfect. Then I guess another question is to Mani and Sabine. Could you elaborate on reaching some of the eco-design guidelines, especially at the beginning? So I guess when you start designing this product or this point of care, healthcare sensor patch, and elaborate a bit on the LCA results.
Okay, yeah, so I think this question is to me probably. So yeah, the LCA results, I've only shown the I've shown the results from a recipe assessment, and I've only shown kind of like broad indicators. But yeah, basically we see a reduction in most indicators, also resource costs, the species extinction, eutrophication, and so on. So most of the, so far, we see most of those things. There are significant problems in a way associated with a life cycle assessment of electronics, and we know this in the EECONE project, and this is what, you know, the teams that work mostly on the work packages that kind of look at eco-design and life cycle assessment do as well. So the guys at Dassault System and Jean-Christophe, who is also in the meeting at Grenoble, they work on the things that are really basically related to the availability of data for electronic components, and that is the major problem that we have. So if we give the results of a life cycle assessment, what makes it really, really difficult is I don't know if I take a different component, will this component give me kind of completely different numbers the next time when I add it to the life cycle analysis instead of one. So there is vastly high data variability. So that's as much, I think, as I can say on the results. We see massive improvement, but again, we need to double check and try to get as much verified and suitable data as possible. The other thing is how we implement eco-design. Well, in principle, we look at the trade-offs we have, but for us it was very simple because all the improvements that we made were already kind of quite already just using the single chip would have made such an improvement on the eco-design that it wasn't, that it's very easy to see the way that you go is the correct way. Obviously, the argument is there is so little design improvement or so little improvement in the use of sustainable materials. So do we really need to use the sustainable materials? But I do think there is much merit in this because as we get better at reducing e-waste in these devices and components, I think we will move towards a future of using more sustainable materials. We will need to replace oil and gas-based materials, and also sustainable materials can be made, like we've shown with the algae, that do not necessarily affect land use, which is a huge component that is often not taken into account as well. So I guess I hope that answers the question.
I think so. Yeah. The data reliability on the one hand side to assess your LCA, it is a big topic, and I guess the way to go is with transparency and see to improve step by step. And the other one is have a holistic picture of your use case, and especially for you, reducing the number of electronic devices brings already a lot of benefit. And then once you reach a level where you cannot improve by reducing anymore, we have to go into sustainable materials. So this is an upcoming topic for us as well. Thank you very much for that. And then there was one more question about this field of working, and I would say if you want to, you can just contact me, and I will distribute your question about a PhD or postdoctoral research to our consortium, and maybe we find something there, because I think it's a great field of working and very interesting and very important. So then I would just have two more things. One is to thank you, the presenters, and the ones that listening to our webinar today. Thank you very much. It is highly appreciated, and I think it's always worth the effort to share our results and to share our side and vision on this. And the very last thing is to invite you to our next webinar. It's in June, and we will have 4 use cases, again, something from automotive, from the consumer industry, and also about aeronautics and aerospace structures. So with that, I'm happy to close the meeting and looking forward to see you in our next webinar. Thank you.